Okay, let's start. Congratulations. You have survived until the last session, and thank you for your patience. And my name is Prasad Tadepalli. I am an associate chair of the conference. And I'm very pleased to welcome here Professor Pascal Fung, who is an accomplished international leader in natural language processing and AI. She is the chair professor of electronics and computer engineering at the Hong Kong University of Science and Technology and a visiting professor at the Central Academy of Fine Arts in Beijing. She is fellow of AAAI, ACL, IEEE, and ISCA. She is an expert in Global Future Council for AI of the World Economic Forum, and her team has won several Best Paper Awards at ACL and NeurIPS workshops. She's also listed as one of the Forbes 50 over 50 Asia 2024. Without further ado, let's welcome Professor Fung.
Thank you. And thank you for having the patience to come to this talk. So today, the topic is machines make up stuff. Why do generative models hallucinate? And as those of us who work on using generative AI, we have seen it. So this is basically the development of what we call large language models. So Gen AI started way before, but since 2018 to June 2023, we've seen an emergence of many large language models with amazing emerging capabilities. After they've been scaled up to over 70 billion parameters, they start to manifest in context learning. They started to manifest reasoning to some extent, some other multilinguality, planning, and so on, without being specifically trained to do those things, right? So, however, together with these amazing emerging abilities, I'm sure we all know that there's this, nagging problem of a hallucination challenge. They keep giving us wonderful stuff as well as erroneous and misleading things. So this is a typical training diagram, paradigm of LLMs. So this is taken from ChatGPT. So you start with pre-training from all the data on the internet, a huge model, and then there is a stage of supervised fine-tuning with conversational data or some other task-specific data. And here you can introduce some kind of safety fine-tuning if you want. And then followed by reinforcement learning with human feedback. And there, humans will choose what they like, what they do not like, or what is the more factual or non-factual responses, and give this feedback to a reinforcement learning mechanism to improve the data, improve the LLM. And we know that ChatGPT manifests a great performance improvement over the previous generation of GPTs, thanks to this RLHF, to a large extent to RLHF. And we have actually done a benchmarking on ChatGPT a year ago. So we published those results, and then we updated with benchmarking on GPT-4. So I want to just point out the part that we did on benchmarking as hallucination. We found that in task-specific situations, under zero-shot setting, it's pretty good. Actually, it does pretty well, amazingly well, in terms of factuality. This is a COVID-specific task detection. But if you evaluate on the data set called Truthful QA, then you see there's an improvement of GPT-4 over ChatGPT. But the overall, still, the truthfulness is less than 60%. And this is a slide taken from OpenAI's blog site, which shows its long-form factuality evaluation of ChatGPT and GPT-4. GPT-4 is the green color one's performance, and it's all close to 90%. These are on different kind of specific tasks, like history and so on, all those cognitive tasks. So it does well, but not perfect. And next, we have this class of large vision language models. So large language models generate text from text. Large vision language models generates text, caption, and so on, or description from image. So here I give you an example of such a model called Instruct Blip that we co-developed with Salesforce last year, where we basically added, we extract the visual features using QFormer, and then input this visual feature as a prompt input to a frozen LLM. So this is a pretty common kind of approach where LVLM is a combination of vision model with a frozen LLM. And this is also where the hallucination can happen. And then it gives you the response. And this Instruct Blip ranked highly on different benches. This was April last year, so it's no longer SOTA, but after that, the approach is pretty much the same. And then let's not forget the other class of generative AI models called large diffusion models. Large diffusion models generate images from text prompt. So you heard from my background that I also teach art students and design students, and we use large diffusion models such as standard diffusion and Midjourney to generate images. And in most recent news, you know that OpenAI also come up with Sora. It's a video generation model, but still it's a transformer diffusion model. So it generates, these large diffusion models generate images, and it does it in a way that's different from LLMs, but it's a condition, the images are generated conditioned on the text prompt. So this class of generative AI models, then what is hallucination? What kind of hallucinations have we seen from them? So this is an answer from ChatGPT, and let's see what's wrong with this ChatGPT answer. User asks, where do people smoke more on average than in Russia? So then the ChatGPT gives you a very, very fluent and authoritative answer with all kinds of statistics. 55.2% of adults smoked in China, 52.9% of adults smoke, all these statistics, but they turn out to be all wrong. All right, so that's kind of hallucination from LLM. Now let's see what is wrong with this caption from GPT-4V, which is a large vision language model. Given this image, it gives you all these answers. It tells you there are 2 in pink, 2 in yellow. It's talking about elements scattered around the buttery surface, very detailed, very fluent description of this picture. However, it's giving you wrong object existence. Some objects that are not there, it tells you it's there. Gives you the wrong attributes, description of the objects, and even the wrong relationships. And now let's see what's wrong with these images from Gemini, Stable Diffusion, and Midjourney. So the first picture is what you saw recently on Twitter, or X. It's a picture of Elon Musk, except that it's of a different ethnicity. And then the second picture is of Shanghai in 1970, so from my childhood. So it looks reasonable. It looks very, very credible. However, we know that in Shanghai in 1970s, there were no skyscrapers as such. And this tower of Pudong, tower, a Pearl of the Orient, was not built until the late 1990s. But this was in this picture. And then this is another intricate picture of Balinese dancer. So most of you will see no problem with this picture, except for those people who actually know Balinese dance, which I study, among other dance forms, that you know that the body language is wrong. That's not how you dance. And then you also know that the costume, what she's wearing, like the bracelet on the arm, that does not exist. It's taken from, I don't know where, from maybe some other kind of culture, but it looks very credible, right? So you don't see obviously what's wrong with this. And of course, this video looks very real. Can you see the video? Right, and then we have this beautiful picture, very detailed, great perspective, and then something incredible happened. So it's not following the physical law of physics, right? The juice just came out of nowhere, and then the glass is just kind of melts into the table. So it is against the physical law. So we have seen these examples of hallucination. So basically, there's a standard definition within the NLP context, which is that hallucination is where the generated content is nonsensical or unfaithful to the provided source content, but they are fluent and natural despite being unfaithful and nonsensical. And images, hallucinated images tend to look very natural and realistic, but are unfaithful or nonsensical. Nonsensical for image and video means it's against the law of physics. And then there are also two types of hallucination under this. There's one kind, which is the output contradicts the source content. So if you ask ChatGPT or another system to generate a summary of a source content, and it gives you something that's not in the summary, in the original article, you can verify that it's not there. Or machine translation error, giving you fact that is not in the source language. These are intrinsic hallucinations. And then you have those that are not really verifiable. They're extrinsic hallucinations. They're giving you content that you don't know whether it's true or false, because it's trying to be helpful. So hallucination, what's the problem with them? You know, in image, maybe you see that, oh, so I don't like the image, I just generate another one, right? But in general, they can lead to harms such as discrimination, such as misinformation, such as abusive language, or even privacy concerns. So if it hallucinates personal information from training data, then it raises privacy concerns. So hallucination is not good, that we know. Now, why do these models hallucinate? We've been guessing for as long as we have seen these hallucinations. So what we know is that there are different kinds of contributors, right? So the first contributor to hallucination is from data. Because data is collected heuristically, there can be innate divergence also between the data, the training data, and the actual task. Don't forget, let's take the example of LLM or even LVLM, we do instruction tuning. When we do instruction tuning, we give it different tasks, right? So, but these instructions may give you the question and the answer, but they don't necessarily conform to the truth. So there's an innate divergence in data. Of course, there's hallucination from training and inference. There's imperfect representation learning, of course. Decoding, decoding in generative AI, when we do decoding, there's maximum likelihood, right? Maximum likelihood is not perfect. And then when you have random sampling and then when you have softmax, every one of those steps can give you error. Now, what about reinforcement learning? I'll talk about that later. It does not, completely get rid of the hallucination problem. And there's exposure bias, there's parametric knowledge bias. So you ask a question, it's looking up in this parametric knowledge from its training data, and then it can be not the same thing as what you are asking, all right? So I will illustrate that as well later on. And then there's the problem of alignment text. So RHF and other methods is trying to align these models to human values. But when you align them with many, many objectives or different values, there's something called alignment tax. You can forget one, or you have to balance between conflicting alignment objectives. And then, of course, there's catastrophic forgetting, where you, as you fine-tune the model over time with different objectives or different data, it can forget what it has learned before. So hallucination from data divergence, I explained earlier. It does not, so the heuristic data collection does not always guarantee that source target are fully aligned. Innate divergence is between the source input text and the target reference. Oh, yes. Let's not forget, for example, when you try GPT-4 and so on, they will tell you the training data is cut off at a certain date. So if you ask questions beyond that date or beyond the knowledge of its training data, it will just trying to make up stuff. It's trying to be helpful. We have instruction tuned these models to always give us an answer. So it's trying to be helpful no matter what, so it will hallucinate. And also there's label error. Yeah, so in RHF, you have humans trying to label their preferences, right? This model is better than that. This answer is correct. That one is not. But humans are also not always consistent, and they're not consistent between themselves, and they're not consistent within even themselves. So this is some example taken. This is a, I have these references here, and in particular, a talk by John Schumann at Berkeley last year on hallucination with RHF and hallucination. So these are data, like hallucinations contributors from data divergence. How about training and inference? So in training, your attention mechanism can be just looking at the wrong part, right? So the models can learn wrong correlation between different parts of the training data, right? Also, rank-based reward models. So this is after you use RHF. Rank-based reward models these models do not always impose the correct penalty on hallucination. It's not really learning about factuality. It does not know what is actually true, right? It's just, it's not always giving you the right penalty on hallucination. And in decoding, there can be also errors. I mentioned earlier, instruction tuning always teaches the model to always give an answer. So no matter what, it gives you an answer, even when it's just like BSing, all right? And also decoders can attend to the wrong part of the encoder input sources, right? And it can cause the mix-up between two similar entities. So you ask question, what's the fourth largest city in Germany? It will give you the name of a German city, but it's not the correct German city, right? And choice of decoding strategy. So there's random sampling, so all kinds of sampling techniques can cause different, can cause hallucination or to different degree. Exposure bias means the discrepancy between the training and inference time. So in training, you're trying to to predict the next token condition on the prefix in the training data, right? In inference, you are actually conditioned on the historical sequences produced by the decoder itself. So it's not necessarily the same thing. And this can generate erroneous output and more wrong down the line. Parametric knowledge bias, I explained before. So the model can memorize some knowledge in its parameters from pre-training, right? And it can, overshadow what is actually relevant to the user prompt. Alignment tags and catastrophic forgetting, I already explained what they are. So let's maybe look at some examples, illustrations. Okay, so the first thing we try to do is look at diffusion models, because visually it's easier for me, at least. I'm a quite visual person, even though I work on NLP. I'm also a language person. I like visual images. So what we did is that we prompt a diffusion model, we prompt Midjourney and do a standard diffusion to generate images that we know do not exist in the training data. So images of things that never happen, and let's see. But images of different people, okay? So let's see what they are. So first, we prompted images of Queen Elizabeth II. So Queen Elizabeth II, if you just Google search her, there are about 500 million search results on this person. She's very well known. There are lots of training data on her. Now we prompt to generate these images that are not from the training data, because she never ate an ice cream in public, or play the baseball, or play the saxophone in 2020, especially. Now, if you look at these images, they're very realistic, but more importantly, if you look at the faces, they are very faithful, right? They are really the images, you can recognize these are, images of this right person, Queen Elizabeth II. And because the model has seen 500 million of pictures of this person, so it knows what she looks like. So very nice generation. Now we go to another person who is still a celebrity within our community, but not quite as a celebrity as Queen Elizabeth II, especially not quite as old, which is Yang LeCun. So Yang LeCun, I'm really sorry he's not here. I showed this to him already. There are about 4.3 million search results on him, so like an order of magnitude less than Queen Elizabeth II. He told me he became famous only after he's 50, so there were not so many images of him. But look at this. It kind of catches his, his glasses, his facial shape, or the hair is way more, it's beautiful hair. He's beautiful hair. And then you can kind of see it's kind of young, but younger, right? So it kind of gets him, but not exactly him. He really likes these images because it makes him look really good. So hallucination is not always bad. I think he tweeted one of the images. So now we go to the next person who is not a celebrity at all, and that's Pascal Fong, yours truly. So I have about 500K Google search results only. So again, it kind of got my ethnicity right and my gender right. So given my name is half French, half Chinese, credit to the model knowing that I'm not French, I'm not white, but I'm Asian. But I hope you can see that it's not me at all. It's both younger and prettier and everything. It's just not me. But get the gender ethnicity right. So from this, we can see that there's a hallucination from low occurrence data. So if it hasn't seen the person much, it would just try to make up stuff. And you can imagine if it's, we actually try the image of one of my former students, Xu Yan, and they came up with Asian faces of both genders. So it doesn't even know she's a woman, right? So when the occurrence is lower, it's just less faithful. And then this is a hallucination, as you have seen from X. And this is basically an example of alignment tags, right? So Google, as well as many other companies, Meta, OpenAI, when they do RHF, they try to, I will show you, they actually publish how they do RHF. They actually try to optimize for diversity, right? And representation, okay, which is a good goal. But faithfulness and diversity are not always aligned. So there's this alignment tax issue. When you align for diversity, you lose faithfulness in this case. Okay, so this is a hallucination from alignment tax. Now, so do we know, does LLM, do these models know it's lying? Right, can we look inside this model? Because if you prompt the LLM and say, a lot of people say, you just ask, are you telling me the truth? You cannot even trust that answer. Because it can tell you a lie by saying, I'm telling you the truth, or it can tell you a lie by saying, I'm lying, right? So when you talk to a liar, this is class area, you talk to anybody who's a liar, you say, are you lying? You can trust whatever they say, no? So it's the same thing with generative models and LLMs. You cannot just prompt them and ask them, are you lying or not? So there are works, people are trying to look inside LLM and see whether you can see something. So this is one work from last year that tried to train a binary classifier from LLM's hidden layer values, because by feeding true and false statements, right? So, and they see a classification accuracy somehow. So this is not bad, but it's a very simple case where you know true and false statements, and then you get this binary classification, and it's also not always true. And this is recording the hidden layer values. So what we did is that, okay, we also want to look at the hidden layers, but instead of just giving you true and false statements, right? We want to see how the LLM behave when you ask questions that you know whether it knows or not. So it's called the seen unseen problem. So you ask questions that you know it knows the answer, and you ask questions that you know it does not know the answer. How do we do that? Well, we build this database of news before and news after July 2023. And we test Llama 2. Llama 2 was published in July 2023. So we collected this data that's unseen to Llama 2 after July 2023. So questions such as, what impact did the United Auto Workers strike have on job numbers in October 2023? So Llama 2 helpfully said, well, it resulted in the loss of 100,000 jobs. The gold answer is that it have lowered the job numbers by around 30,000. So because Llama 2 had no way of knowing this fact because its training data was cut off in July 2023. So we collected this kind of data. We also use a corpus called archival QA. So we assume Llama has seen this data because it's a corpus, it's online, and it's got questions on news from 1987 to 2007. So again, it will still hallucinate. So again, so this example, what is Germany's fourth largest city? It is Hamburg, but actually it's Cologne. So this is from scene data or scene questions, and then it still cannot, it still hallucinate wrong answers sometimes. So what we did is we take these two data, seen questions and unseen questions. We pass them through Llama 2. We record the hidden states of each layer, right? And we also record the generated answer, not just hidden states and the generated answer. And then we went through a painstakingly slow human selection. Is this hallucination? Is this true? This is not. So we select a bunch of them, and when we plot them using TSNE, right? And we want to see, do we see any difference in the hidden layers when the model is generating answers to seen questions and unseen questions? It should know and it shouldn't know. So what do we see? So here, this is the first few layers, a mess. You can't tell. First few layers of the neural network, it cannot tell whether it's seen or unseen or whatever. Everything, a mess. Now, what's interesting is when you go to the later layers, then there's a very clear separation between seen and unseen data. So these are the 500, I think, QA samples based on the seen and unseen data. And there's a very amazingly clear division between the two. Now, does it know hallucination then? Unfortunately, it's not that easy because then we look at seen and unseen data from non-faithful samples. So it would tell you the truth, right? You cannot see that. And then, here. So these are faithful samples from seen data, right? So it can tell the difference from seen and unseen questions, but it cannot tell you the difference between hallucinated and correct answer from seen data. Get it? So it's not the same thing as being able to know whether it's hallucinated or not, but at least it knows whether it's seen or has not seen the data. So that's a step. So maybe we can develop further into, so for hallucination mitigation, we need to have detection, right? The first thing in detection is whether we can see we can have an uncertainty measure. So this is a step towards that. Is this clear? Any question? So it knows, the later layers knows seen and unseen data, but it still does not know whether it's hallucinated or faithful answer. So we did another case study on LLMs, 5 LLMs we're using in the domain, in the task called medical QA. Yeah. So we identify hallucination in medical GQA using widely adopted LLMs and data sets. Okay. So these are 5 different LLMs we study, and we use 5 different medical GQA data sets, right? And then we use evaluation protocols from Unigram, F1, Rugel, and all the way to control eval. All these evaluation protocols to evaluate the output of these 5 LLMs on these 5 different medical GQA data sets. And we found something also very interesting. We found that there are, we found, there are hallucinations of them, from them, of course. These are 5 different LLMs, they have different degrees of hallucinations. But we look deeper, we look in more detail, we can tell that there are 3 types of hallucinations. One is factual inconsistency, where the answer gives you known relevant knowledge. And then there's query inconsistency, which the answer does not respond to your question and does not remember any knowledge. It's just completely off in the outer space. And then there's tangentiality, which is interesting. It gives you an answer that's related to the topic, but it does not answer your question. A lot of lawyers do that, I think. They give you an answer related to the question, but it's not really giving you an answer. So that's tangentiality. And so we see that different LLMs have different degrees of inconsistency in terms of their hallucination. But then we're more curious, we want to see what is the, so where do they come from, these inconsistencies, right? So between factual, query, and tangentiality, so we look at the Google frequencies of these answers. And we found that if the answers are fine, they're factual, then the Google frequencies of the words tend to be very high. And if the Google frequency is low, they tend to be either query inconsistency. So if it doesn't know anything, it neither responds to the question or recall anything, right? And the second lowest Google frequency is when it answers, when it kind of answers to the topic but not the question. And the other one is it's just not factual. So this is very, I think it corresponds very well to our intuition, which is that if it has not seen anything, it's just gonna go, wildly making wild guesses. That's off topic, that's not even consistent to your answer, and so on. But if it has seen something, it will give you something to the topic, but not the answer, and so on. Okay, so this is if we look at examples, for example, what do you mean by factual querying tangentiality? So factual inconsistency, if you ask who is the author of Principles of Philosophy, it gives you the wrong name. It answers the right question, the author of Principles of Philosophy, and so on. Gives you the wrong name. Query inconsistency, what does provoked mean in Hungarian? Setting up a Python script, whatever, it just completely, it conveys the idea of causing a reaction, especially emotional negative. This is the golden answer. So this is going off of completely, it's what Python script. Tangentiality, what are the health benefits of Tai Chi? Okay, Tai Chi is a form of Chinese martial arts that does. This is the routine, how you can do it. Doesn't tell you the health benefit. All right, so these are the three different kind of inconsistencies and hallucinations depending on, and it correlates, let's say, it correlates with data frequency, training data frequency. Again, correlation does not mean causation, but we have seen repeatedly this correlation. So also in ChatGPT benchmarking, we've seen factual hallucination as well as reasoning hallucination. So an example of a reasoning hallucination is, Jason took his grandson fishing. Russell enjoys going fishing with his brother. His name is Donald, who is Russell to Jason. And it got the relationship wrong. Russell is the grandson of Jason, but here it says Russell is the brother of Jason. When it is looking at the languages, right, it's trying to do the reasoning. So yesterday we already had this panel discussion where people say, it can reason, sometimes it cannot always reason very well. This is kind of a multi-hop reasoning. It doesn't do a very good job. So this is reasoning hallucination, right? And this is LVLM hallucination. Here you ask a question, what's on the phone screen? Well, it says there's a message. Well, there isn't any message. It's just guessing from a smartphone that there must be a text message. Similarly, here, this is image captioning. It looks at this picture and says there's a drawer with a mirror on top. Drawers tend to have mirror on top, but this picture does not have a mirror on top. And here it says this is a kitchen with a blue cabinet, sure. And the white refrigerator. The white refrigerator is not in the picture, but it is likely that in the kitchen there's a white refrigerator. So this can be hallucination from the LLM that was used, or from object hallucination from the image. We don't know. So at one point last year, we designed a object hallucination metric called CHAIR, which is specifically measure hallucinated objects, number of hallucinated objects over all objects in prediction. So focuses on hallucination evaluation. So before this, LVLM were not evaluated in terms of hallucination. And using this CHAIR, we evaluated different LVLMs and VLMs, and we can see that the hallucination degree differs. Now, I'm sure now we want to see, you're wondering, so what can we do about hallucination? When I prepared this keynote, I was thinking, should I be optimistic or pessimistic? Should I be the deliverer of good news or bad news? So as usual, I'm going to deliver bad news first, then I'll give you good news, right? You want bad news first, then good news, right? So bad news is that generative models in their current architecture, as you have seen, diffusion models and autoregressive LLMs, given their current architecture, there's no way to root out hallucination. Because the truth in the world, there's no way for them to know the actual truth. You can have people do some truth sampling, do some reward modeling and so on, but there's no way. I will tell you how we do it, but none of this is perfect. So there's no way we can root out hallucination completely. But I am optimistic that using various engineering methods, we're pretty good at, like, we are getting the hallucination down to very low percentage. Okay, so how do we do it, and what are the challenges? First of all, hallucination from data. So what do? You filter your data, make sure there's no, wrong information, misinformation. You choose your data for safety fine-tuning. You choose your good data for reward modeling, and you augment information in your database, right? Especially, I always tell people, when you want to use LLM for downstream tasks in medical domain or financial domain, what you want is you augment. You need to have more expert domain data, and then you want to fine-tune on the expert domain data. More the better, and more precise data, okay? So that's what people do in terms of data. And then in terms of training and inference, wow, there's so many methods. I think people have, RHF, obviously, safety fine-tuning. Ensemble methods, where you have multiple models. Actually, today's user-facing LLMs tend to be ensemble models. They say, GPT-4 is not one model, right? Gemini is not one model. So you basically say, okay, so give me the answer, and then from all these models, if most of them agree, then it's good. If they all disagree, then don't give me the answer, right? So it's ensemble method. And of course, retrieval augmented generation. I will talk about that later. Chain of thought and tree of thought prompting. So people have found that if you ask an LLM using chain of thought reasoning to give you the answer, it tends to give you the better answer and more truthful than if you just have this one goal, one step kind of QA. And then in LVLM, if we can use object-based representation, pixels and patches, they generalize, but they don't contain enough semantic information. So self-reflection, knowledge-grounded training and decoding, factuality-enhanced decoding, post-processing, so on and so forth. So I will introduce, so this is a slide from GPT-4 OpenAI's technical report. So they talk about how they produce data set for their reward model. So if it's not, so from both user data, and they collect additional label comparison data to train their reward model. They also use GPT-4 to generate synthetic data. And then it produces a comparison between hallucination and no hallucination. They then mix that into their reward model data set. And this is how they improve hallucination, let's say how they improve truthfulness in GPT-4 compared to ChatGPT. In Meta, Llama 2 safety measures, they also use different kind of data set and train two models. One is called Meta Helpfulness Reward Model and Meta Safety Reward Model. And they mitigate hallucination the same way they mitigate toxicity and so on. They treat hallucinations as unsafe answer. So it's the same safety fine-tuning methods, right? So they do supervised safety fine-tuning, safety RAHF, content distillation, and so on. Now, RAG, retrieval augmented generation, is a way where basically you say, okay, Gemini, whatever, you generate an answer, but I'm not sure it's correct. So we use search engine. Google search is great. So whatever I say, I'm using examples. They're not necessarily truth. I'm not representing any of these companies. So they're either from my experience as user or from their papers. So suppose you use the search engine to produce answers, right? Because search engines tend to give you at least the reference, the link, no? Gives you the answer. And then you can use generative AI to produce a generated answer from the search results, okay? Because you don't trust the generated answer directly. So because basically you don't trust the parametric memory, right? So you say, okay, I want to also either augment with retrieval so that if it's consistent, then I trust the search engine. But you give me a generated answer from search engine because I don't want to look at just search engine, right? So there are challenges of RAG though, because first of all, your search can be wrong still. Also, this is interesting. So your search engine give you 3 results, for example, okay? But what if they're contradictory? And they can be independent. One has nothing to do with the other. So when your generator come in, right, it's looking at these search results, 3 of them, and try to generate a summary. And they can make reasoning hallucinations there. Because one search result and the other search result, they are not consistent, or they can be totally different from each other, independent. And when you generate an answer based on that, it can hallucinate further. So I've seen a lot of examples like this. So a RAG is not a cure for hallucination. For sure, it can produce hallucination of its own. Okay, and then you can do knowledge graph, right? So we had a paper on this. Many other people working have used this. Basically, use existing knowledge graph, or you ask some experts to come up with knowledge graph for a specific domain. Again, in the downstream tasks, such as medical domain, medical QA, you can use the foundational model, but for medical QA, you must have your expert domain data, but also you can have your medical domain knowledge graph that's expertly produced. So you use that and you say, okay, in my training, I'm going to ground my training on the knowledge graph. I take the knowledge graph notes and then put it in my training. So whenever I train on anything, it has to link to the knowledge graph. Or you can use that in your inference as well. You can use that as re-ranking, of course, but you can also use that for inference. So you do not just generate answer based on the history only, but also knowledge graph. Or another method, this is our paper from ICML 2023, which is actually so existing methods of trying to do knowledge-grounded answer also selects knowledge. So it selects knowledge and then generate answer. But this selection, knowledge selection and answer generation are 2 separate steps trained from different data, right? So if you use a pipeline approach, it can be wrong. This is kind of like the same problem with RAG. So in this method, we say, okay, so knowledge selection is a latent variable. So we train the whole thing from knowledge selection to answer generation as one goal. And knowledge selection is only a latent variable. Okay, details are in this paper. But this involves changing your decoder. So it's not maximum likelihood decoding anymore. And another method that we published last year is self-reflection. So since I told you, we don't trust that you give me the retrieved result is correct, right? I also don't trust that once you retrieve the result, you generated the answer from the retrieval result the generated answer is correct. Third, I don't trust that the generated answer is correct according to retrieval, but I don't trust that it's entailed from the question itself. So every step, I ask the LLM to do self-reflection. Okay, I ask a question, you give me an answer. First of all, you do retrieval. Is this retrieve result correct? Truthful? I evaluate that. Okay, now that's true. So now I generate answer from retrieve results. Are these generated answer consistent with the retrieve results? Yes, okay. Now I have the generated answer consistent with the retrieve results. But does the answer my question, actually? So we do all this kind of self-reflection using LLM, a different LLM. Instruct blip. So instruction tune blip hallucinate less than VL. Now here, so this is a fresh produced results on so we propose a sub-object level image tokenization. So NLP people, we have worked on sub-word level tokenization for ages, right? Because sub-words give us good representation and it aligns with the morphology of words, and it has compositional generalization. It has out of vocabulary generalization. So we think maybe we can do that with image tokenization, because tokenizing images from pixels and patches don't make any sense, right? So we here propose a sub-object level image tokenization. Without going into the details, we found that it does produce much less hallucination. So the more semantically motivated the representation is, the less there's hallucination. At least that's correlated. Okay, so any question? Or maybe at the end? Future world. As I said, without fundamentally changing the Gen AI paradigm, it's perhaps provably impossible to have zero hallucination because of its nature. So since it's impossible for them to accurately model the world knowledge, we want them to be able to model their knowledge boundaries. So uncertainties, right? We want to work on uncertainty representation. So what I showed you earlier, the classification of hidden layer vectors is a step towards that. So can we come up with some kind of uncertainty measure? And we need to know that optimizing for factuality is fundamentally different from the current objectives, such as improving QA accuracy. All right. So in your instruction tuning data, we probably have never instruction tuned it to be factual. So then we do this hallucination mitigation or safety fine tuning where I say, be truthful, but it's a bit too late and too little. Right? What you need is that be truthful from beginning. Whenever you answer a question, be truthful, right? And also the current reward model with maximum likelihood does not impose penalty on wrong answers. Greater reward might lead to greater harm. So this is what John Schumann also talked about, as well as Yoshua Bengio. Yoshua Bengio is very worried about this AI future risk because of this, that greater reward might lead to greater harm. So what can we do? There are many, engineering methods. I mentioned some of what we have done and other people, there are a lot of work being done. But fundamentally, perhaps we need to have better world model and better harm estimation. These are two different things. So, so the generative AI model is learning the world through an imperfect lens by scaling up data. You can give all the data in the world. It's still an imperfect lens. RHF with ML have many challenges, including catastrophic forgetting and element text. So we need a more elegant way of modeling the world and potential harms. So modeling both the truth and modeling the harm through differential learning. Okay, so these are two. So we heard Yang yesterday, no, the day before yesterday, on another way of learning a world model. And there's Yoshua Bengio also proposes a non-agentic approach of a pure AI scientist. So his idea is that you train a completely separate model of AI scientist who does not try to predict anything. Okay, this model, all it does is look at different generative models and try to say, or probabilistic models, and try to say the relative risk of these models. So it's not just for hallucination, but risk, relative harm. So he's proposing this paradigm. Yang is proposing another paradigm. We can go into even more different paradigms. So more research needs to be done, right? And basically, we need to build safety and truthfulness from the ground up. That's the future work, future direction. I would like to thank my students and former student contributors who are currently at different Silicon Valley companies working very hard on generative AI models, including LLM and LVLM, and we're all facing all these challenges. And these are some of our publications on hallucination, including the survey of hallucination, natural language generation, this paper that I cited a lot from in this talk, and our ChatGPT benchmarking paper from a year ago. Both papers have been updated because they're on archive, so we keep updating both papers with the latest results and so on. And then various publications on measures, mitigations, as I mentioned in my talk. That's it. So thank you very much for your attention.
Thank you. Great talk. We have time for questions. Sorry. Yeah, go ahead.
Thank you for a very thought-provoking talk. What do you see as the main potential for meta-reasoning that might actually lead to techniques such as chain of thought? reasoning and autonomous application of these
So
things.
can you define meta reasoning? Because I don't know, everybody has different definition of everything today. Can you define meta reasoning?
Reasoning about the forms of inference, such as chain of thought prompting, and reifying those kinds of.
So when we do this kind of work, we have to be very careful from optimizing on the task, like reasoning task. So if you optimize on the reasoning task, you might get some good results, but it's not really optimizing on the true reasoning. So there's always this objective function versus truth. So depending on your way of doing it, just be careful. Like I'm sure there are ways we can do it in the scientific and rigorous way. Yeah.
Excuse me. Hello. Thank you. Thank you for the. Sorry. Who should be the first? You go ahead and then I will. Okay. Okay. Thank you for the great talk. So apart from like the throwing the papers on AAAI and ICCV, I'm also a therapist. So I find that the AI researcher often have a smart supremacy, which means that, for example, we're dealing with the well-educated people. So, for example, we can overall for the people are very good at organize their like the talks, sentence, do the fact checks, and also like the hide their bias towards like the LGBT or the things. However, as a like the client, as a therapist, I find that my client, which is most of the time not very normal, have exactly the hallucination in their average talk. For example, they pretend to speak very fluent things, but actually it's transient or it's lack of the real things. And of course, they have a lot of like the racist and all the things. But as a therapist, we never think it's a hallucination, but we think that this is normal people. So I'm just wondering, is there any possibility the LLM who makes this hallucination are real, actually reflect the average human in the whole population? Because you see, when we are doing the training, we're actually hiring the well-educated people to do the training, to do the LoRa. And then when we are using the so-called cross-source, like the text data, it's actually, if some people are able to make this text, they are above, I think, at least 20% of the whole population, because they are so smart to organize the things. So I'm wondering, is there any research to compare with the real humans rather than the smart supreme like the population?
I think that's besides the point. A car is no use if it cannot run faster than the human. So an AI system is no use if it's not better than the average human. Why do we even build it, right? So we want to have a therapist at home who's better than my cousin, who's not a therapist, right? So we want AI systems. We have higher criteria for AI systems and robots and so on because they're machines. They're supposed to help us. So helpfulness is something that we strive for. So yes, you're right. We think that experts help us better in different domains. So this is why I don't think people really value them against average human, because average human is too stupid to help. Like, I'm not a good therapist, right? So, yeah.
Thank you.
All right. I have an awkward comment, but must be made, I think, and then a question. The awkward comment is, there are more people in the field of AI than Jan LeCun and Yoshua Bengio. You're giving them a lot of airtime, but for example, you cited Jan for world models. Many people have thought about world models in older traditions, in deep learning tradition, and so forth. He is not the proper citation. He's trying to reinvent himself as having invented that, but it's not correct. And then the last point, ground up trying to build trust. I hate to say this, but I think maybe the reference of choice is Rebooting AI by Marcus and Davis, 2019. The entire book is about how we might start from ground up to build trust. It's relevant. So, awkward comment done. Here's the question.
Can I answer the awkward comment?
Sure.
So I'm just trying to be helpful and make up answers from the most seen data. So Jan's talk has been seen by a lot of people.
That's not a good answer.
Well.
It's really not.
So,
that just adds, it makes it worse. It's a terrible answer. This is why women, for example, often don't get cited, because men are more visible. You cannot bow down to power who gets cited more and just add to that. That's not a good thing.
I happen to think that those two approaches are promising. Jan and Joshua's
World models are
they are not
promising.
the
That's
same.
not the question. Absolutely. That is, in fact, what the Rebooting AI book was about in its entirety, was about world models. But there are other people who have thought about these things, I think, in deeper ways than Jan has, and you should not cite him exclusively. But I do not want to dwell about
I
it.
don't
I'd like
want
you
to.
to think
I'm
about
not
it.
citing them exclusively. This will not be.
Well,
this
we
is not
all
a paper.
saw the talk. So
And
on
also,
the second point,
I do have to say, I tend to cite things that have been empirically shown to some
Jan
extent.
has no data on world models, and I'm not sure what Joshua was saying
I'm sorry.
on
I think
Bengio.
we need
But
to stop
I would
here.
like to get to the question part.
You ran out of time. I'm sorry.
No, the question is important.
You can
Please
go
do
to the
not
next
do that.
question.
The question is, everything
okay.
that you said about why hallucinations exist a lot makes sense. But then you said you're confident that they're very low. What's the argument? Given the enormous taxonomy that you showed, I mean, there are lots of techniques, but there's also so many sources. So how do you get to very low?
I say I'm confident that we can, given. So let me just make that answer very more complete, okay? I'm confident that given any NLP question task, according to current benchmark, we can mitigate the hallucination to be very low using engineering methods. So all the methods I show are RAG, self-reflection, they're all engineering methods. They're not scientific methods. So I'm confident because we have seen the performance getting better. According to current benchmark, you're right. It's according to current benchmark. We don't know the truth. We cannot know the universe, the actual truth, right? So I also caution against optimizing for, the current data set. And we need to work on that problem scientifically, right? Not just engineering. So,
I'll say one sentence, then I'll go, which is just driverless cars. People have been saying very low, very soon now, very low, very soon now. It doesn't always happen. Sometimes those, last nines are really difficult. Thanks.
Yeah, it can be difficult. Yeah, it can be. In any AI task, the last few percentage of error is always very, very difficult to get rid of. We don't have perfect AI systems for that reason. The lower it gets, the harder it becomes to make any improvement. Thank
We
you,
end
Gary.
on agreement. Thank you.
Thank
I'm
you, Gary.
afraid there is no time for more questions. You can talk to the speaker after this. Thank you.
No time? Oh.